Okay, 1.2, we're going to be talking about defining limits and using limit notation. So this is one of the more important, well, everything's going to be important that we talk about this year, but you can't really skip any part of it, but this is the foundation. So the idea of the limit is what's going to allow us to define calculus, really. So it's really important to, right off the bat, be comfortable and understand what the notation means and with the overall idea of the limit. So let's jump in. Defining limits and using limit notation. So we're going to represent limits analytically and use correct notation, and then interpret limits expressed in analytic notation. So first thing I want to say is that the idea of a limit, it is a process, okay? It is not a constant. So the idea of a limit is figuring out what are the y values of a function doing as we approach a certain x value. And that word approach is going to be the key. So I want to know what the y values do as we get really close to 2. And so you can just think about this in a tracing motion for this one. All right, so if I'm tracing along that curve to where I'm approaching the x value of 2, I would come in this way. And then what do my y values seem to do as I get closer and closer to 2 on that curve? Well, they seem to approach 4, at least from that side. Okay, well, what if I approach 2 from the other side of that curve? Well, I'm just coming down from the top, also seems to approach 4. Pretty simple idea. The big idea here is I don't really care, when I'm talking about limits, I don't really care what's going on at 2. I care what's going on as I get closer and closer and closer to 2. What are my y values doing as I get infinitely close to 2? And that's really the calculus part of this, right? So calculus is the first part of mathematics that starts dealing with infinities and infinitesimals. So super large and super small numbers that we can't treat as actual numbers, we treat as a process. So if I want to get infinitesimally close to 2, when will I reach 2? Never. But can I determine the behavior of the y values as I get infinitesimally close to 2 on this curve on the x-axis? Yes, the y values seem to have some pattern. From both sides, they seem to approach 4. So I want you to think of a limit as a process of getting infinitely close to something. All right, so then with that in mind, we can kind of summarize what we just figured out as the limit of x squared minus x plus 2 as x approaches 2 equals 4, meaning as we approach 2 on the x-axis, our y values, which are determined by this formula, approach 4. And so we use this notation generally. All right, let me move there we go. So this is an intuitive definition of a limit. There is a formal definition that you would need to know if you take like an analysis class, which is a couple of years down the road if you continue with mathematics. But the intuitive idea is that a limit exists if as an x value approaches some constant, the y values approach some other constant. And so we say the limit of f of x as x approaches a equals L. We call a the limiting value. We call L the limit. So the limiting value is the thing we're approaching on the x-axis. So generally what it means is we can get as close as we like to L. We can make our function get as close as we like to L as long as we take our x values sufficiently close to a. So you can make a game of it where I'm like, okay, how close do you want to be to L? And you say, I want to be within 0.1 of L. And I go, okay, as long as you are within 0.0001 of A, your y values will always be within 0.1 of L. And so as long as there can be a rule on the x-axis be this close to A, and you will always be this close on the y-axis to L, then we say that the limit exists. I know that's a little confusing, but I'll give you some visuals in a bit. Let's break down the notation. As I mentioned, notation is extremely important at this level in math. And so here's our notation. And once again, let's see. This is called the limiting value. And so as x approaches that value, f of x is our function, L is our limit. So as x gets closer to a, what are our y values getting closer to? L. And I want to point out again that it does not matter what's going on at a. What matters is the behavior of the function as we approach a, as we get closer and closer and closer to a. In all three of these cases, the limit of f of x as x approaches a is L. And that's because the behavior as we approach a, as I trace along this curve and get closer to a, from either side, my y values are always getting closer and closer to L. Now this one, at a, the y value is defined as something else down here. Doesn't matter as long as I'm talking about a limit. So let's say we call that m. In this case, f of a actually equals m. But I'm not asking what's going on at a, I'm asking what's going on as we get closer and closer to a. Well, as we get closer and closer to a, the y values get closer and closer to L. So this limit still holds. Same thing here. Here, f of a is undefined. It's just a hole in the function. Still, as I approach a, as I get closer and closer to a on that curve, from either side, my y values get closer and closer to L. So my limit of f of x as x approaches a is still L. Okay? When we talk about limits, we care about what's going on with the y values as our x values approach something, not what's going on at that value. What does the behavior look like it's doing as we approach that value? So let's do an example. State the limit verbally and explain what the equation means intuitively. All right, I'm going to pause it and I'll write it out so that you don't have to watch me sloppily write a sentence. Okay, so pretty straightforward verbal limit here. This is read as the limit of g as x approaches 5 is 2. And what it means intuitively is that on my function, as my x values get closer to 2, on either side, as my x values get closer to 5 on either side, my y values get closer to 2. Now, there are infinitely many functions that could satisfy this limit, but I'll sketch one for you. So let's say that this is 5 and this is 2. There are a bunch of different ways this could look, but I'll just draw one. Great. So as x gets closer and closer to 5 on this side, my y value seems to get closer to 2. And from this side, as x gets closer and closer to 5, my y value still seems to get closer and closer to 2. All right, this one's a little interesting, a little challenge, but I think you guys can maybe get an intuition for this. So state the limit verbally and explain what the equation means intuitively. And if you are struggling with it, we will go over it in class next time, but go ahead and at least give me a verbal statement of what it means. Pause it here. If you can, try and kind of sketch a graph that would satisfy this. Okay, so one-sided limits. Hopefully these will feel a little intuitive. As we've noticed, each time that I evaluate a limit or that I talk about a limit, we are approaching our limiting value from two sides, from the right and from the left. So that warrants defining a one-sided limit. So we have a little notation for this. Whenever you see, oh no. There we go. Whenever you see a little superscript of a minus, like this, we call that a left-hand limit. And all that means is that we are only looking at what's going on as x approaches a from the left side. So it's a minus because where are the negative numbers? On the left side of the graph, right? And then likewise, a right-hand limit, we have a superscript of plus, and we call that a right-hand limit. And in that case, we are only looking at what's going on as x approaches a from the right-hand side. So you don't need to worry about what's going on from the left in that case. So let me show you what I mean. All right, here's an abstract example where the limit of f of x as x approaches a from the left. And that means, again, we are coming in from the left side of a. So as we approach a from the left, my y values approach L. And that's what they're trying to say here. That's a y value of L. And then again, the limit as I approach a from the right, that could look something like this. Now I'm coming in from the right of a, also approaches L on this graph. Okay, so the big idea here is there's three things we talked about, right? The overall idea of a limit, which is just what are the y values doing as the x value gets close to a certain number. And then we talked about one-sided limit, what happens when we approach from the left and what happens when we approach from the right. And so the big idea that we're gonna come up with now is that for this to exist, for the overall limit to exist, it's gonna have to be true if and only if the limit from the left is equal to the limit from the right. They have to approach the same thing for us to say that the overall limit exists. If they don't approach the same thing, then we can only talk about limits from one side or the other. If they do approach the same thing, then we can say that the overall limit exists. All right, so I want to show you a little GeoGebra video to kind of show you what a limit looks like in action. So here, look, my green point, which is on this graph, is going to approach, I'm going to approach this blue point at 2. So what I'm looking at is this function here, and I'm going to let x approach 2. Now from the right, we'll pay attention to green. From the left, we'll pay attention to purple. The green O and the purple X are going to show you what's actually going on with the Y values as these points trace the curve. And so I'll just let this play. So what's going on as X approaches 2? So as our X values approach 2 here, you can see that our Y values approach the limit, which is something a little above -3. So our x is approaching 2 from the right and the left, our y clearly approaching the same value, which is -2.8. Since they approach the same value from the left and the right, we say that that overall limit, which is in red, exists. If these approach different y values, we would say the overall limit does not exist. All right, back to it. Let's talk about a very famous function. This is called the Heaviside function. This is very famous in electrical engineering, and it's because it basically is a graphical representation of a switch in an electrical current, where 1 is on and 0 is off. And so it's a piecewise function that's defined as h of t is 0 if t is less than 0, so t being the x-axis, so it's 0 if t is less than 0 here, and it's 1 if t is greater than or equal to 0, so that point is filled in, and it's 1 here. So it says verbalize the following equations and explain what they mean. So give me a second, I'll write out the verbalization, and then we'll talk about what they mean. Okay, let's start here on the left. So down here on the left, I said the limit of h as t approaches 0 from the left is 0. And that just means as we get as we come in from the left towards 0, our y values are approaching 0. Now, our y values are constant in that case. They just always are 0, but they are also, we would also say they are approaching 0. Note once again, it does not matter that it is undefined at 0. I do not care what's going on at the limiting point or at the limiting value. I care what's going on as we approach the limiting value. And as we approach the limiting value, our y values are always 0. On the other side, the limit of h as t approaches 0 from the right, so I'm coming in at 0 from the right, is 1. And same reasoning, our y values are all 1 there. It doesn't matter that it's defined as 1 at 0, it just matters that as we approach from the right, it is 1. And so, as we just discussed, this would mean overall that if I asked you what's the limit as t approaches 0, and I didn't put a superscript or a subscript there h of t, we would say it does not exist because the limit from the left does not match the limit from the right, and that's going to be a prerequisite for the overall limit to exist. All right, you give it a try. State I'm covering up part of the directions. State verbally, and then explain what the equation means intuitively. Go ahead and pause it here, try that. You can give a sketch of that, and we'll go over it in class. Okay, and the last thing is I'm making this formal statement. You'll come to understand that in this class, when something's in a blue box, it's extremely important that you write it down because it's a theorem or a definition. I've already referenced this, but here's what we say. The limit of f of x as x approaches a equals L if and only if the limit as x approaches a from the left equals L and the limit as x approaches a from the right equals L. So for the overall limit to exist, it has to be approaching the same value from both sides. If we're approaching different values from either side, we would say that the overall limit does not exist. The one-sided limits do exist, but the overall limit does not exist. All right, well, I hope your first flipped classroom experience went well. We'll work on the problem set in the next class.